Okay, so now you should be a bit better at balancing chemical equations. And we'll want to remember that the process of balancing a chemical equation, that's done in order to fulfill the law of conservation of mass. So you may wonder, how exactly do we report the mass of a compound? Well, we do this normally using something that's known as the formula weight. And this is the sum of the atomic weights of all of the atoms that are present in a compound. So we take sulfuric acid as an example here, H2SO4. We would simply calculate the formula weight as 2 times the atomic weight of hydrogen, since there are 2 of them, plus the atomic weight of sulfur, plus 4 times the atomic weight of oxygen, since there are 4 oxygen atoms. Now I can simply get these atomic weights from the periodic table. We talked about calculating atomic weights in chapter 2. Well, we can simply take these values, all given in atomic mass units, and come out with a value here of 98.09 atomic mass units as being the formula weight of a compound. And this is one way that we would talk about the mass of a compound. Now, another term that is probably much more familiar than formula weight is something that's known as the molecular weight. Now, molecular weight is just equal to the formula weight for a molecule. And so in some ways, these terms are interchangeable. A molecular weight is a formula weight for a molecule. So why would we not just use molecular weight for everything instead of using formula weight? The reason is that ionic compounds, we remember, are not described by molecular formulas. They're described only by empirical formulas. And so it would be incorrect to refer to something as the molecular weight of an ionic compound, even though it's commonly done. It's incorrect. Really, that weight would be just the formula weight, since ionic compounds are described only by empirical formulas. Now, another term that's useful when we are keeping track of mass is the percent composition of a molecule. This is essentially just of the total mass, what percent of that mass comes from each of the individual elements. And this is useful because we often do characterization methods that allow us to calculate or determine or measure the composition, the percent composition by mass of different elements in a molecule. And so we need to be familiar with that term. The way that we calculate the percent composition is we simply take the number of atoms of that element that we're interested in times the atomic weight of that element divided by the formula weight of the entire compound and multiply that value by 100%. So a very quick example here, if we calculate the percent composition by mass of oxygen and hydrogen in table sugar, we can do that separately. So common table sugar, sucrose, C12H22O11. So we have a lot of atoms present. We can do this simply by taking the number of oxygen atoms, 11, times the atomic weight of oxygen, which is 16, divided by the total formula weight for this compound. So if you added up all of the masses of carbon, hydrogen, and oxygen, you would come out with a formula weight of 342. And then we basically take that value and multiply by 100%. We can find out that oxygen by mass composes slightly over 50% of this molecule. We can do the same thing for hydrogen. What we find is that although there are 22 hydrogen atoms compared to only 12 carbon or 11 oxygen atoms, there is nevertheless, this only makes up 6.4% of the entire mass. So this is how we would go about calculating the percent composition by mass of an atom present in a molecule. Now, there's one other term that is vitally important for us to understand, and it will also help us when we want to relate the mass of compounds in terms that we are more familiar with. So I listed the masses previously in atomic mass units. It would be much more useful to relate that in terms of more familiar unit like grams. And this is where this term comes, the term of the mole comes in. If we look at just a tablespoon of water, in that tablespoon of water are contained approximately 2 × 10⁻³ water molecules. This is such a ginormous number of water molecules, and it becomes extremely inconvenient then to talk about stoichiometry, keeping track of mass in terms of the number of molecules that are present. This is just all written out with all of the zeros present, clearly an extraordinarily large number. And so this is where we come to this new unit, which is written as the mole. It is sometimes just abbreviated as MOL rather than MOLE. I'm not entirely certain why, but it is frequently abbreviated like that. And 1 mole is defined as exactly the number of atoms present in exactly 12 grams of isotopically pure carbon-12. It turns out this number, 1 mole, is equal to 6.02214 times 10⁻³ objects. Now, this has come to be known as Avogadro's number, since it was proposed by Amadeus Avogadro. And it is often written as 6.02214 times 10⁻³ inverse molar, because it is simply the number of objects per mole. Now, Avogadro's number is just another conversion factor. It's number of objects per mole. And so 1 mole of carbon-12 atoms would be 6.022 times 10⁻³ carbon-12 atoms. 1 mole of water molecules is 6.022 times 10⁻³ water molecules. Or 1 mole of nitrate ions would be 6.022 times 10⁻³ nitrate ions. We can talk about 1 mole of anything, and it's simply 6.02214 times 10⁻³ of those objects. This is extremely useful now because rather than talking about the individual number of number of molecules, we can now talk about a much more easier unit to use, much more manageable numbers, which with many less decimal places or powers, in terms of talking simply about number of moles. Now, since we have that unit, 1 mole being a certain number of objects, we're now able to relate atomic mass units conveniently to mass. So the atomic weight of an element that we get from the periodic table, which we had previously reported simply in AMU, or atomic mass units, that is equal to the mass in grams of 1 mole of that element. We'll go through some examples here in a moment. The formula weight of a compound is equal just to the mass in grams of 1 mole of that compound. So it's no longer just in atomic mass units. We can now talk about this in terms of grams per mole. That's essentially what's known as the molar mass, or the molecular weight. Again, that term's coming in here. Molar mass as now being grams per mole, and that's equal to the formula weight, which is listed just in atomic mass units. And so that's an extremely useful way to use those values to now relate to something that we're more familiar with, known as grams. So let's go through a few examples. What's the molar mass of glucose, for example? C6H12O6. Well, first we find just the formula weight. So it's just 6 times the atomic weight of carbon, plus 12 times the atomic weight of hydrogen, plus 6 times the atomic weight of oxygen, and we can find those values just from the periodic table. We thought previously, we talked about those previously as being just atomic mass units, but 1 AMU is equal to 1 gram per mole. And so if we add all of these up, we come out with 180.18 AMU, but AMU is also just equal to grams per mole. And so my molar mass here is just 180.18 grams per mole. Now how does that come in useful? Well, molar mass, just like Avogadro's number, is just another conversion factor. It's another equality. There is 180.18 grams of glucose in 1 mole of glucose. Remember that 1 mole is another equality or conversion factor. 1 mole of glucose would be 6.02214 times 10 to the 23rd molecules of glucose. And so I can use this just as an equality and another conversion factor. Let's go through a couple examples. So how many glucose molecules are present in 4.51 grams? I have glucose, which I can actually order online, and it's just a sugar. And I measure out a little bit, a scoop, maybe a part of a teaspoon, maybe a teaspoon of that weighs 4.51 grams. And I want to figure out then how many molecules are present in that. Well, this will be simply like a unit conversion. So I start with figuring out first the molar mass. So I have to figure out what my conversion factors are. And we've done that previously. So this is, again, I can write this as an equality. 180.18 grams of glucose is equal to 1 mole. That's my equality. And so I can write it as a conversion factor with moles on top or moles on bottom as needed. Additionally, I have Avogadro's number, which is 6.022 times 10 to the 23rd molecules per mole. And so I can simply write that as an equality where I've got 6.022 times 10 to the 23rd molecules is equal to 1 mole. That's, I can write as a conversion factor now with moles on top or on bottom as I need. So those are my 2 conversion factors. And I start by putting my known value in the top left, like I normally would for a unit conversion. And so I write 4.51 grams over 1. And then first I write my first conversion factor that involves grams, and that's this top one here. And I put grams on bottom so that it will cancel with the grams that are currently on top. So I write 1 mole over 180.18 grams. This is my first conversion factor, and I write it this way to cancel the grams. That leaves me with a certain amount of moles. And then I use my second conversion factor that involves molecules and moles. I'm going to put moles from that second conversion factor on bottom, molecules on top. That will cancel the moles. I multiply through and I come out with 1.51 times 10 to the 22nd now molecules. This is very useful and something you should become very familiar with doing, converting from grams to moles, converting from moles to grams, converting between molecules and moles, and end up being able to convert between molecules and grams and molecules using these conversion factors. This is the power of the unit mole, and knowing that the molar mass or grams per mole conversion between that and simple atomic mass units that you would get from the periodic table.